Let's start. Our next speaker is Professor Drazen Adamovic from University of Zagreb. The title of his talk is Realization of Affine Vertex Algebra and Logarithmic Vertex Algebras. Please.
Thank you very much. Thank you very much to organizer for the invitation to talk to Qing, to Malihe. So it's my pleasure to speak here. So I need to share screen, no? I need to share screen. Yeah. Okay. So something is. Okay. Sorry. Okay. So can you see? Just. Can you hear me?
Yes, we can hear you.
So thanks again. So I will speak about some recent result about representation theory of affine vertex algebra, and I'm very happy that Jinwei had talked before me. So he already introduced many important notion and concept. So idea is to study representation theory or infinite dimensional algebra. So this is one basic problem. We all are interested in that problem, but there are various techniques. And one technique is using this concept of vertex algebra, vertex operator algebra, and I will demonstrate how this concept can be useful these days in solving certain problem. So what is our basic object here? So this is we start with simple Lie superalgebra, and then we have the associated affine Lie superalgebra. So this is infinite dimensional Lie superalgebra, and somehow we are interested in the representation theory of this infinite dimensional Lie superalgebra. But so there are various categories of representation of this infinite dimensional Lie superalgebra, and most of them can be catched by the vertex algebra approach. So usually in the Lie theory, when we study representation theory, we instead of study a module for Lie algebra, we study module for Lie universal and developing algebra. But in the affine setting of affine Lie algebra, this universal and developing algebra is too small. It's too small, and it's difficult to understand representation theory using this universal and developing algebra. Instead, we use so-called universal affine vertex algebra. So we have this universal vertex algebra somehow which controls the category. So then we consider then the category of representation of the affine vertex algebra. Affine vertex algebra catch all smooth or also called relaxed module for infinite dimensional superalgebra. But essentially representation theory of this algebra is the same as representation theory of this vertex algebra. So vertex algebra is uniquely generated by such formal Laurent series x of z acting on this representation space, and this is exactly like in Jinwei talk. In Jinwei talk, he considered Virasoro case. So in the Virasoro case, vertex algebra is quotient of Verma module by one singular vector. Here again, this universal affine vertex algebra is the quotient of Verma module by certain singular vectors, but it has a very nice description as this induced module. So we have two structures. One, this algebra is a representation space of certain algebra, and we have a field state correspondence, which you start from vertex from the vertex algebra and act on a module. But for application, we need to consider smaller algebra. This is simple quotient. So this universal vertex algebra has infinitely many modules, but in general, this simple quotient is much smaller. And we are interested in the representation theory of this. Physicists also, from their point of view, also consider such kind of representation, but when they say that they consider vertex algebra, they usually think about representation theory of this simple vertex algebra. And now we should the notion realization of vertex algebra. What this means? Realization of vertex algebra means that instead of this algebra, which is although well defined, very mysterious. It's very mysterious. What is the structure theory and representation theory? We want to replace this algebra with something simpler. I think in mathematics it's always the idea to study complicated objects by certain simpler objects, not to go into difficulties. So we want to study, instead of this vertex algebra, we want to study some free-field algebra. And free-field algebra are usually lattice vertex algebra, Clifford vertex algebra, also called BC system in physics literature, Weyl vertex algebra, also called beta-gamma system in physics literature, their tensor product and localization and so on. So this is the mean. And what happened in the 20th century, in the last century? So we know that vertex algebra started somehow in 1980, around 1980, and axiomatic theory started in 1988 or something. So people study this vertex operator realization without theory of vertex operator algebra. So this was Lepowski-Wilson. This is maybe first paper about explicit realization. Then Igor Frenkel, Victor Katz paper, Alex Weingel-Frenkel. So all of them write certain vertex operator formula, and this vertex operator formula also appear without this algebra. For example, for toroidal cases, here is Svara Rao. So we have toroidal representation also done by vertex operator construction. So this is somehow basic object in the theory of such infinite dimensional algebra. But in this case, all these realizations are later interpreted using language of vertex algebra. So everything can be interpreted later of vertex algebra. But what really happened? We have only few levels. So for example, this cases covers only level 1 representation of affine Lie algebra, and here have level -1 representation. So there are plenty other cases, and I was interested how this theory can be extended to new example. So but then we came to new century. We all live between two centuries, essentially, have knowledge about 2 centuries. So some new mathematics came. And this new mathematics is this famous quantum Hamiltonian reduction. And this is the bridge between affine vertex algebra and W algebra. So this is related to Qing Wang remark and Qing Wang discussion about Virasoro, affine. So they are related with this quantum Hamiltonian reduction factor. This is one idea, a new idea how this works. So take any nilpotent element of Lie algebra, even element if it is Lie superalgebra, and any complex number C. Then one can associate the universal affine W algebra. So this is completely, now we are in completely new language. we have affine W algebra. So something we have, this is good, well defined, but very, very complicated. But in any case, we have this new family of algebra, which are vertex algebra. Not in general, they are not Lie algebra. They're just vertex algebra. This is the process called quantum Hamiltonian reduction. But everything is good defined. So then we can consider simple quotient. Simple quotient. We have simple vertex algebra. Simple vertex algebra, and then we can ask: do we have inverse? Can we go in opposite side? Can we invert quantum Hamiltonian reduction? And what does it mean, inverting quantum Hamiltonian reduction? But we are essentially, good news is that this quantum in the inverse of quantum Hamiltonian reduction is even much more nice than quantum Hamiltonian reduction itself. So we essentially expect that for each simple affine vertex algebra, we can embed this into tensor product of this W algebra with some free field. So this is inverse quantum Hamiltonian reduction. This program is not finished. It's not finished. This is relatively new stuff developing in last 5-6 years. So question is, do we have and we expect that this we will have positive answer, and we will always have such embedding. But you notice this is much better when you have tensor product. Tensor product is perfect things. This is just tensor product of two vertex algebra. Quantum Hamiltonian reduction is you take complex, you have and then you take cohomology, which can be more complicated. And this inverse quantum Hamiltonian reduction is essentially answer on the question, what is realization? What is realization? So in many special cases, this W algebra collapses, simplifies. It can be one-dimensional. Simple algebra can be one-dimensional, and we can just embedding to this free field algebra. Okay, and now I can speak about solution and possibly application of this. And this story is fully solved in full generality for SL2 and SL3. So for the SL2, SL3, we know almost everything. For high rank case, there are some result, but some correspondence is still unclear. So for what happened in the case of Lie algebra SL2? In the Lie algebra SL2, we have bridged to Janeway algebra, which Janeway investigates. So there are no only one choice. We take either. So we have 2 by 2 matrices. We have unique one nilpotent element, and we do reduction, and we get Virasoro. So it's called all the minimal reduction or principal reduction gave you Virasoro. So you have a functor from the SL2, affine SL2 vertex algebra to the Virasoro vertex algebra. In the case of SL3, we have two options for nilpotent element. We have 3 by 3 matrices. We can choose either a so-called principal nilpotent element, and then we go so-called Zamolodchikov algebra, if we take minimal nilpotent element, we get so-called Breshatsky-Polyakov algebra. So everything was defined even before concept of vertex algebra, but now we can prove theorems using that. So I want to recall, but just to show what is this Breshatsky-Polyakov. I skip about Zamolodchikov. What is this Breshatsky-Polyakov algebra? So Breshatsky-Polyakov algebra is universal vertex algebra generated by 4 even fields. One is Virasoro. We have Virasoro. Here you have Virasoro central. This is operator product expansion of this Virasoro commutation relation. Then we have Heisenberg field. We have Heisenberg algebra. We have Virasoro algebra. This is Virasoro. Heisenberg. So we have Heisenberg Virasoro inside of this. But then we have two fields, G plus, G minus, and commutation relation can be understood using this operator product expansion. But what is not good news, this Brzezinski-Polyakov is not Lie algebra in usual sense. So in Lie algebra, when you commute two generators, you finish in linear combination of other generators. But you don't have square. But here you see here, if you commute G plus and G minus, you have square of Heisenberg here. So it's not Lie algebra, but we have theory. We can develop representation theory like for Lie algebra. We have high-square representation theory and everything good to find. So this is this algebra one for which is important for our story. Okay, and now what is now this free field algebra, which we will use for realization or for inverting quantum Hamiltonian reduction. And now we are lucky. Now we are lucky. This algebra in many cases, so it is something which appear in the paper of Qing, Wang, of Yuli Bilik and Xiamen Tan paper about, and it's closely related to toroidal case, although we don't study toroidal cases, but they are closely related. So we start from some hyperbolic lattices, hyperbolic type lattices of rank 2, and then we associated lattice vertex algebra of rank 2 to this hyperbolic lattice. So we have lattice vertex algebra, but then we just take half of lattice element, and then we consider tensor product of the Heisenberg, which is always called M1, but rank 2 Heisenberg, we just rank 1 lattice. This is also called half lattice VOA. And there is another interpretation of this algebra pi 0. This is localization of the Weyl vertex algebra. So Weyl vertex algebra, Weyl algebra is a well-defined, nice object in the representation theory, and we can localize it in one. If we choose localization with this element EC, then we get exactly this pi 0. So there are two, and we know a lot of stuff about weight category. What a weight category? We know a lot, but in any case, there is one. But what is interesting here? This is now not rational. So Gino has mentioned rational. So this VL is rational, but this P0 is not rational. It has a lot of modules. It has, for example, Whittaker module. So we have Whittaker module. We can consider this Whittaker type of module. So this is so here we have this beta 0 VL is lambda V WL, but or 1 over lambda WL. And this we have free field realization of this Whittaker type module, and it is irreducible for this pi 0. So with this pi 0 we can do representation theory, weight representation theory. They even have logarithmic module, but now I will just show this Whittaker type of module which exists for this pi 0. So this is our free field algebra, which we need for using inverse quantum Hamiltonian reduction, and then we go case by case. Now we go case by case, and we inverse Hamiltonian reduction formula for the SL in the SL2 case are done in my paper published 4 years ago. So we take this SL2. This is affine SL2, and then this minimal reduction is just Virasoro vertex algebra explained by Jinwei. And this is a funny formula for this Virasoro. Central charge is 1 minus 6k plus 1 square over k plus 2. So this is the formula, and it works for each k, not critical, not critical. But what we can prove that when we have k is not integral, so we need to exclude integral case. There is a reason is because of behavior of quantum Hamiltonian reduction of an integrable module is not well. Then we have non-trivial embedding of simple affine algebra instead of tensor product of the Virasoro, simple Virasoro vertex algebra with this central charge, tensor with this pi zero, so this localization of Weyl vertex algebra. So, and there are very nice formulas are even not complicated. So we have nice formula for E, nice formula for H, and nice formula. F is a little bit complicated, but still more operational. And then we can embedding of one vertex algebra in tensor product of two. And as we see, everything is related to this Virasoro. Essentially, everything is done in Virasoro language, done by Jinwei, can be translated using this inverse reduction to SL2 case. And there are plenty of application of this. Plenty of application. I will just study application, for example, for Whittaker module. For Whittaker module, so just recall definition, since there here are experts for Whittaker module. If I said something, I learned definition of Whittaker from Xiamen Zhao. So assume that G is Lie algebra with triangular decomposition. We have triangle there, any Lie algebra finite and infinite dimensional. We have G, n minus H and n plus triangular decomposition, and we take any Lie algebra homomorphism from n plus to C. Then the universal Whittaker module with Whittaker function lambda is defined as quotient of universal enveloping algebra by this left ideal generated by x minus lambda x1. So this is something similar like High-Thread module, but a little bit a relaxed condition of High-Thread to get Whittaker module. And one question in the representation theory is describe if this VL bar is irreducible, or if it is not, do we have simple quotient? How many simple quotients do we have? And describe these simple quotients. So this is the problem, how to determine the selector of V lambda. So this is now a completely different word, and I will show that this concept of inverse Hamiltonian induction is very useful here. It's very useful here. So we have in SL2 case, this is even simpler. So this n, so we have affine Lie algebra type A11. This n plus is generated by A0 and A1. And Lie algebra homomorphism for n plus is uniquely determined by two numbers, lambda 0 and lambda 1. So classical Whittaker module are parameterized by this lambda 1 and lambda 2. And now we should have explanation what is this universal, what is simple, and what is universal is described in joint paper with Rentsei Lu and Xiamen Zhao. It's almost 10 years when we wrote this paper. So assume that case not critical, and we have non-degenerate case, then the universal Whittaker module is irreducible. So in the non-degenerate case, the universal Whittaker module is irreducible. But so this was nice, and we nicely published this paper. But then the question was, what happened with in the case of degenerate Whittaker function? And what is interesting that this degenerate Whittaker module could be module for this simple affine V algebra obtained by by this inverse Hamiltonian reduction. Just briefly. So there are various methods. One method is let us consider now all Whittaker. So if the general case, we have plenty of Whittaker submodule, and let us kill all and take a simple quotient, but there is nice answer using this inverse quantum Hamiltonian reduction in the same paper. So in this paper, what happened? So we can construct all possible degenerate irreducible Whittaker module as a tensor product of M tensor PL, where M is highest weight, irreducible highest weight module for the Virasoro algebra, and P lambda is this Whittaker module for this pi 0. So then this module is Z-graded. So this model is Z-graded. It's weak model for the vertex algebra, and in that way we can construct almost all possible this degenerate Whittaker model. So using this inverse reduction, we see what will be possible way to generalize this. This is nice. So we in order to generalize this, we should study higher rank case and try to understand what is happening in higher rank case. And this higher rank case, just to see now that we have now a realization in SL3 case. So in SL3 case, this is a paper with Kreuzig and Genera, published this year. We can use this Breshatsky-Polyakov algebra and then we have inverse Hamiltonian reduction of affine SL2 is embedded into tensor product of Breshatsky-Polyakov, which I presented before, tensor with this Weyl vertex algebra, beta gamma system, and pi 0 as before. So in this case, we essentially representation theory of SL3 is controlled by the representation theory of this Breshatsky-Polyakov, and this Breshatsky-Polyakov has some similarity to affine SL3. So this is just how we should go, and probably this is the way one can approach more general case by using such kind of inverse quantum Hamiltonian reduction. Okay, if there is some question. Okay, and now I was discussing a lot. So in any case, now I go to second part of my talk on this logarithmic vertex algebra. So this logarithmic vertex algebra is also mentioned slightly in Jinwei talk, when Jinwei mentioned about Virasoro, about 1P models. 1P model is essentially related to this triplet vertex algebra. So they are classical logarithmic vertex algebra. Studied in physics. Theory started in physics, but later I wrote several papers with Anton Milas about that, and we learned that Thomas Jinwei they now include everything in tensor category story. I'm very happy because of this, because now we have better understanding of everything. But in any case, this triplet algebra is nice vertex algebra, and it is somehow again related to Virasoro. So it's, you have computing dual pairs of SL2 and the Virasoro, and this triplet is huge extension of the Virasoro associated to these 1P models. And we prove that they are C2 cofinite and non-rational, they have projective module, and so related to quantum group. Then we have doublet algebra, which is extension of this triplet with one simple module. We have singlet, also mentioned with Jinwei. Singlet is U1 orbifold of this triplet, which has, again, enough nice interpretation. So there are these classical logarithmic algebra, which we studied around 2008, 2013, and prove something. And now, after 10 years, people again study this using tensor category approach. But what is important that this algebra is not very much generalized. There exists high rank generalization, but still theorems are just for this rank 1 case. So and then what is good with this logarithmic algebra? We have lattice, explicit lattice realization. So we take generalized lattice vertex algebra or abelian intertwining operator algebra, and then take the kernel of one operator called screening operator acting on this lattice algebra. We get doublet, and we have Virasoro algebra, and we have triplet algebra. Again, it's a kernel of this screening operator acting on this VL. And now, so these are classical. This is just classical story. And then we Qing Wang wanted to solve one problem about Lie superalgebra OSP 1-2 at critical level. We have problem at describing what is parafermion, what is the structure, we have this, and it turns out that for doing that we needed to do some deformation of this. Okay, sorry, I have one more slide. And before that, we use this inverse Hamiltonian reduction to extend this Virasoro type algebra to affine SL2 type algebra. We have this VP algebra. Also mentioned, this paper was mentioned by Jinwei. And then with this, so this is classical logarithmic algebra, I will call. And then we with Qing consider some dual logarithmic algebra. And as I mentioned, although this it looks abstract, we will see that we will solve one nice problem about Lie superalgebra using this method. So you see here that we have Virasoro element. So this element of the lattice vertex algebra will generate Virasoro algebra. And then, but what we can do with the form with this Virasoro element. With the form, we add one lattice type element to this algebra, and we get new action of the Virasoro algebra. And now this action is completely different. Then we change the screening operator. Then we get new type of screening operator, and with the screening operator, we consider a kernel of these new operators, and we get new doublet and new triplet. We get new doublet and new triplet, and more. But what is we get new type of algebra? So we completely change our algebra. This new logarithmic algebra are not the same as old, but they are isomorphic as a Virasoro module. So this is one thing which is interesting. So we have this completely the same decomposition of this logarithmic algebra as in classical sense, but the algebra are not isomorphic. They are not isomorphic as vertex algebra. They are isomorphic as a Virasoro algebra. So we found explicit isomorphism between this AP and AP nu, and this is the formula for this automorphism. And then we extend this SL2 in the SL2 case. In the SL2 case, we get extension of this -2 + 1p SL2 algebra inside of this tensor product of AP with pi 0, and get this inverse type reduction realization of this VP nu, and get new family of vertex algebra which are not isomorphic, but they are isomorphic as SL2 model. So we have VP nu and VP isomorphic as a SL2 module, but not isomorphic as a vertex algebra. So this is our abstract reformulation of certain result of it using this different Virasoro element and different approach. And what are application? What are application? And application is very nice. In the case P equals to 2, this old, so with the case P equals to 2, so let P equals to 2, we get minus 2 plus 1 over 2 is minus 3 half. Minus 3 half. And this minus 3 half, we get realization on one, the small n equals 4 vertex superalgebra at central charge C equals to minus 9. So this is one n equals 4 algebra, which also appear in physics theory these days, and in this relation between some physics theory with vertex algebra. But for us, it's more important that this V2 nu, this new alpha is just OSP at the critical level. So we use whole this theory to describe this, what happened with the orthosymplectic vertex algebra at the critical level. So we get this, and then we can go back and we see that this VP nu, so in this case P equals to 2 OSP and N equals 4, they're isomorphic and SL2 module, so they have completely the same decomposition, the same character, so everything is similar. But and we can completely now understand this branching rule was not known before, but for us it's most very important to find this connection between N equals 4 and this OSP at the critical level. Critical level is just how many, just in 2 minutes to say what is this N equals 4. This N equals 4 superconformal algebra is maybe the largest, at least superalgebra, almost there is large N equals 4 algebra which can be constructed. It is algebra generated by Virasoro field, SL2 triple, which I denote by J0, J plus, J minus. This is even part, and we have what means N equals 4. We have 4 primary vector of conformal with G plus 3 half, and they are satisfied the following lambda bracket. This is Katz notation lambda bracket, which can be transferred to commutation relation. So this is normal least superalgebra, infinite dimensional. And this is fantastic that this is related with this OSP. You know, all we know what is a least superalgebra OSP, and how we relate this. So we show that this critical level OSP algebra has the structure of irreducible module of V2 of N equals 4 superconformal algebra generated by these fields. You see, so this we have complete formula. Our duality gives complete formula. What is the relation between OSP and this N equals 4 algebra? And we can go in opposite direction. If we have N equals 2 algebra, we have the structure of irreducible module of SL of OSP by using this the even simpler formula. So this is our duality, but this duality was used to describe critical level OSP. This is our main purpose, and the next job for us is how to generalize this, for example, for OSP 1 to N, where we still don't have complete understanding what is behavior at the critical level, and so on. Okay, thank you very much.
Thank you very much, Drazen. Thank you. Let's thank our speaker.
Thank you.
Thank you very much. Is there any question or comment?
Hi, Drazen. Are you working on the? Oh, by the way, the inverse induction is called Drazen Drazen functor, Adamovic functor. So are you working on the high rank cases beyond SL2 and SL3?
So about inverse reduction. So these days they are formula. You mentioned you were in Dubrovnik conference. We have Dubrovnik conference in when it was 2 months ago, last month.
Yes.
So we see that David Rideau, his student, Zach faculty, presented inverse reduction formula for SLN.
Oh, okay.
For SLN, but he cannot prove irreduced simplicity of realization. But so that formula for SLN or something. So in any case, this higher rank beyond SL3 is formulas are much more complicated, but still they are not simplicity result. We can here prove simplicity of relaxed module or everything which appear. Even this SL3, for example, the relaxed module, we can construct a relaxed high-weight module with such that top component is Gelfand-Zetlin module of arbitrary dimension. So this is even this case is much more complicated. So but somehow this simplicity, but this I think in a few years it will be done for all SLN case, all data, but then you have, as you mentioned, problem of fusion rules and tensor category.
Okay, thank you.
Thank you.
Is there any more question or comment?
Hey, Drazen. Yeah. So in your paper, you mentioned your paper CMP 19.
Yeah.
So there you give a irreducible module. It's a degenerate radical module. Is that a let's see, generalized Walmer module or?
Oh, okay. I can share the screen again. Sorry. So this is. Can you see it? Yeah, I include this about Whittaker because so see in this. So what is our story? We have a realization of this SL2 in tensor product of the Virasoro with this pi zero.
Yeah. So
and then with this pi zero, we have Whittaker module, which also appeared in our paper in 2016 with Whittaker module. And what we do, we tensor this Whittaker module with pi zero with arbitrary high-weight module here. With arbitrary high-weight module.
Yeah. Here. No.
And then we get our degenerate, and we can prove and by using this technique. So this realization is very good for proving simplicity. So this is, as I mentioned. So we have this high-weight module for the Virasoro. High-weight module for the Virasoro. It tensor with this Whittaker for P lambda, and we get all degenerate, almost all. Maybe we should use automorphism, which change E to F to get all. So we get irreducible. So this is description of the simple quotient of the simple and this is essentially very nice. So tensor highest weight module with P lambda, we get our degenerate case. Yeah.
This is say lambda 2 is equal to 0. Lambda 1 is non-zero. Lambda.
Yeah.
Lambda is non-zero.
Lambda 1. Yeah. We get.
Yeah, lambda 1 is non-zero. So this is a degenerate radical module, but for so you got a irreducible one, but actually it seems you have, if you know maximal submodules, there are different maximal submodules.
I put this remark. I didn't study, so this is a good point. So in the paper, so instead of so we can construct first universal.
Yeah.
So here this M is irreducible highest weight module. So irreducible highest weight module. But if this Virasoro highest weight module is highly degenerate, so we can. So what we can do? We can take this highest Verma module. We take Verma module for the Virasoro, which infinitely many singular vectors, and then you see that each singular vector in this Verma module will be new Whittaker module. So we essentially have everything happen on this Virasoro part. So this is complete translation between Virasoro and SL2. So all Whittaker modules happen. Of course, I cannot exclude that there is some generalization, some non-tensor product module as we know, but
what is the center? The central charge? The central charge is non-zero?
No, central charge is non-zero. It's almost arbitrary. So central charge is C.
Oh, it's dk.
Dk always put K.
Okay.
This is central charge
So
reduction.
since say lambda 1, lambda 2, if one of them is non-zero, is zero, the other one is non-zero.
Yeah.
This is actually it's more complicated. So if both of them are zero, then you only get highest weight modules.
Yeah, this is
okay. Thank you.
Thank you.
So Drazen, I want to follow Professor Zhao's question in that screen. Can you share the screen?
Okay.
Just now.
Okay. And which page do you want? This? Can you see?
So in this theorem, you should exclude the critical level case, right? In this theorem.
Yeah, this critical, but we did critical with coming, is it? So in this critical level, this is one dimensional.
Okay.
Yeah, I think in this critical, but again in this critical SL2, in this critical SL2, so we have I didn't include this, but in critical level, universal for the universal, we can put here W algebra at the critical level. This is commutative. This in this SL2 case. In this SL2 case, W algebra is commutative, so we can take any function of this commutative algebra, and then we tensor with this pi zero Whittaker module, and at critical level we can get all Whittaker standard Whittaker.
Okay. Thank you.
Thank you.
Okay. Is there any question or more comments? If there is no, let's thank Drazen again. Thank you.
Thank you.